Hello, so today I'm going to do this very tough integral from the MIT integration bee. I'm going to do a solve where we can generalize this integral into many other families. So we're going to even get some classics out of this. Now, how are we going to do that? Let's first of all rewrite this integral as a function of a. So we're going to get the function of a is equal to an integral from 0 to infinity of e to the power of minus ax times sine of 3x all over x dx. So all we've done there is we've made this 2 a general a so that we can work with this function. Now the first step in this solve is going to be differentiating this function. So we're going to get f of a, or actually the derivative of f of a is going to be, and then we're just going to ignore that this is an integral. So this is Feynman's trick, or differentiating under the integral sign. So if you haven't seen that yet, well, it's pretty powerful in a lot of cases. So what is it going to look like? We're going to get a minus sign because of the chain rule, and then we're going to get e to the power of minus ax times sine 3x times x all over x dx. So notice that we are differentiating with respect to a. That's why we have to use a chain rule on this exponential function here. And all of the other x's are just constants. So that might seem confusing, but definitely don't get it mixed up. This is why we're going to get that times x just as a constant from the chain rule. Now, obviously, we can cancel some stuff out. Let's see. We're going to get times x and divided by x. So let's just scratch that, and we're going to get this new integral. And this integral is actually solvable using integration by parts. So let's get that set up. So we're going to use the DI method for integration by parts, where we have this sign column where the sign constantly switches. So that's going to give us 1, minus 1, and 1. So as I said, that's just switching the sign each iteration of differentiating or integrating. So what function are we going to be differentiating? We're going to use e to the power of minus a times x. Now, we're also actually going to take this minus sign in front of the integral in there as well, just to make things a little bit easier later on. And then we're going to integrate sine of 3x. Now, next up, just two derivatives here. So now we are going to be differentiating with respect to x, which is going to give us a times e to the power of minus ax. And then the second iteration is going to be minus a squared times e to the power of minus ax, like so. Now we're also going to be integrating as well. So the first integration is going to be minus 1 over 3 cosine 3x. And the second time is going to give us minus 1 over 9 sine 3x. Now, if you want to check that yourself, you could actually just integrate or differentiate in this direction, and then you're going to find the correct derivatives. So that's just the same as integrating in this direction. Okay, so if you don't know the DI method, it might be a little bit confusing about, what have we actually done here? The point is that we read this table diagonally, like so. If we are taking it just as a function that we need to evaluate, not integrate, evaluate. So, for example, this, and then this, and we keep doing that until we want to stop, and then we read it horizontally and we integrate. So sometimes we just get a 0 in this differentiating column, for example, and then we just integrate 0 so that then the whole process stops. But in this case, we actually can't really stop that process, so we do need to get an integral. So which integral are we going to get? Now, maybe let's first get these parts that we need to evaluate. So the first part is going to be this, and we're going to have to multiply those together. So minus times minus is going to give us positive. So we're going to get 1 over 3 times e to the power of minus ax times cosine of 3x. And then we're going to evaluate that from 0 up to infinity. And then the second part we're going to need to evaluate is, is this. So let's see, what's that going to be? Again, multiplying two minus signs, so that's going to give us a positive a over 9, and then we're going to get e to the power of minus ax times sine of 3x evaluated from 0 to infinity. Now don't forget that we actually still need to write down our integral, but we're first going to evaluate these two functions. Let's start with the easiest one. So what happens in this case when we plug in 0? Well, the exponential function is just going to be 1, and the sine function is 0, so that's 0. What happens when we plug in infinity? Well, we're going to get an infinitely small function from the exponential function, so that's also giving us 0, just taking the limit as x goes to infinity there. So it doesn't really matter what sign does, e to the power of minus ax is just going to give us 0. So this entire part is 0. Now the second part here is a little bit more difficult. Let's first of all see what happens at infinity. Well, that's just going to give us 0, just because of the same reason as in the last case. Now what happens when x equals 0? Well, now we're just going to get, from the exponential function, e to the power of 0, from the cosine function, cosine of 0. So that's both 1. Now it is a lower bound, so this part is actually going to equal minus 1/3. So we're going to get minus 1/3, and then we still need to write down our entire integral. So again, we read this horizontally like this. We're going to get the integral from 0 to infinity. Again, two minus signs cancel, so we're going to get a plus of a squared over 9 times e to the power of minus ax times sine of 3x dx. Now let's just take this constant out real quick. And now let's notice some particular things here. Now mainly that actually this part here is going to be minus our derivative. So notice that this function, or this integral and this integral, are exactly the same, but we have this minus sign here. So let's just plug that in maybe. But first let's get rid of this column. So we're going to get that f of a is equal to minus 1/3 plus a squared over 9. And then again, these integrals are the same, so we're actually going to get minus f of a like so, or actually the derivative of f of a. And now we actually have this sort of functional equation, basically, just in terms of the derivative of f. So what's that going to give us? Let's first distribute this minus here. So we're going to get minus and then plus here. I'll just get rid of the brackets like so. And now we're going to get this moving this part over here. So the derivative of f of a plus a squared over 9 times f of a is equal to minus 1/3. We can factor a derivative of f out here. That's going to give us the derivative of f of a times 1 plus a squared over 9 is equal to minus 1/3. Now let's just bring this part here in the same numerator. So that's going to be 9 plus a squared over 9. So the derivative of f of a times 9 plus a squared is going to equal minus 3. And then let's move this part over as well. So just dividing by that is going to give us the derivative of f is going to be minus 3 over 9 plus a squared. Now that we have that, we're actually really close to a very nice answer here. So what are we going to do? We've got this derivative of f, but we don't need this derivative, we need the function itself. Notice first of all that actually this is already very powerful, because we can actually solve an entire family of integrals, not the one we need, but this family of integrals is now solved by using this. So what do we need to do to get our f of a here? We're just going to need to take the antiderivative. So let's do that. Let's take the antiderivative. So f of a is going to equal the antiderivative of minus 3 over 9 plus a squared dA. Now, this is a fairly standard integral, but I'll go through the solve anyways. So what are we going to do? We're actually going to factor out a 9 here. So we're going to get minus 3 times the integral of dA over 9 times 1 plus 1 over 9 a squared. Now, the next step is to bring in this 1 over 9 into this square. So we're going to get 1 over 3 times a squared. And now we can actually apply substitution. So we're going to get 1 over 3 times a is equal to u, which means that 1 over 3 dA is equal to du. So almost trivial. And let's just fill that in. Notice that that means that dA is equal to 3 times du. So we're going to get minus 3 times the integral of 3 times du all over 9 times 1 plus u squared. Now notice that all these constants just make the integral of du, or actually minus du, over 1 plus u squared. Now this integral is very standard. If you don't know it, don't worry. You can look it up quickly, or just take the derivative of arctan and you'll figure it out. So this is minus arctan, and then of course we can't forget plus c. Now we're almost there now. So we're so close to the answer, but we have this problem with the c. So let's maybe rewrite all of what we've done here. Let's get rid of all of this. And let's just substitute back in 1 over 3a for our u. So this is equal to minus arctan of 1 over 3 times a plus c. Now, notice that we've got this unknown c. How are we going to figure that one out? Because now we could plug in a equals 2, and then we get the desired integral, but we still have this unknown. So what are we going to do? We're going to take a limit. We're going to take the limit of our function as a goes to infinity. So the limit of f of a. Now, what's that going to equal? First of all, let's consider our expression here. When arctan goes to infinity, we get minus, or we get pi over 2, but in this case, we're going to get minus pi over 2 plus c. Now, what happens when we let a approach infinity in this integral? Well, again, this exponential function, just like when we were evaluating these other functions, is going to give us 0. So that actually just means that this entire integral is going to be 0. Notice that the bounds don't affect that. And now we can actually see what c is. So this means that c is equal to pi squared over 2. And we can fill that in into our function here. And now we can just plug in whatever value of a we would like. In this case, we would like a equals to 2. But again, we can plug in any value. So let's write down the integral that we actually needed. So the integral from 0 to infinity of e to the power of minus 2x times sine of 3x all over x dx is equal to pi over 2 minus arctan of 2 over 3. So a really nice answer here in a very generalized form. Now, maybe one last thing to notice here, we could actually generalize even more by using a random variable for 3 here. So that would be the integral from 0 to infinity of e to the power of minus ax times sine of bx all over x dx is equal to pi squared over 2 minus arctan of a over b. So really awesome answer here. Now, one thing to maybe take into account is that both a and b have to be positive. It's not too difficult to make b, for example, negative. Still get an answer. A does always need to be positive because otherwise this won't converge. Now, one more thing actually to get even more families of integrals is we could keep differentiating this function f of a and get even more functions. So really nice general form of answer here. Thank you so much for watching. I hope you enjoyed this very tough integral. Till next time.